All right, we're back with looking at some of these exercises that have two trees. And so let's look at another example. So remember the basic idea here, just like the last video, is to consider two different but related probability trees. One will start with events including A, and then they'll have some conditional probabilities such as B given A for second tier edges. The other tree will start with events, say maybe including B, and have probability of A given B among their second tier edges. And remember that the probability of A intersect B, in other words A and B probability, is the probability of A times the probability of B given A, but it's also probability of B times the probability of A given B. And this two ways of doing this intersection makes a connection between the two trees. It's the probability of a path in each of the trees, so it's going to be the probability at the end of the tree. So all those probabilities at the end will be the same in both trees, perhaps mixed up in a different order. And so this information can be tracked in contingency tables as well as the probability trees. And so this is what we're going to do. We're going to try to track this in both things, and some of the information, the joint probabilities, can be illustrated with the Venn diagrams as well. So let's take a look at this and see if we can make sense of this. Okay, so here's a pretty practical example. Suppose that there is a horrible disease in which 1% of the population have it in a particular area. Now let's suppose there's a test for this disease which will correctly identify those with the disease 97% of the time. It will produce a false positive, that is, say somebody without the disease has it, 4% of the time. So it looks like a pretty good test. Now construct two complete probability trees that are related and the related contingency tables for this situation. In particular, we're most interested in the probability that a randomly tested person, say somebody who walks in from a wellness test, so a randomly selected person, suppose they test positive to the disease. What's the probability that they have it? Now, at first glance, you say, well, 97% of the time that test is good here, only 4% of the time a false positive. You might say that there's a pretty good chance that they have the disease. But let's work it out and see if that's true or if that's not true. Okay? So start by setting up the two trees without any probabilities and just set up your two-way contingency table with the headings in it. So set up your headings, and let's use these letters. Let's use D for the disease, and not disease we'll say H for healthy. And then they can either test positive or negative for the disease. Let's call that P and N. So set that up. Don't try to write any probabilities in it yet. Just kind of get the structure set up. Okay? Go ahead and do that and come back when you're ready. Press pause now. Okay, did you get this? So one tree says we put disease or healthy first, then follow that up by testing positive or negative. The other tree we have set up the other way around, okay, and that we're going to have it either they test positive or negative, and then it's going to have the diseased or healthy second. And in our table over here, we have diseased or healthy are the two columns, positive and negative are the two rows, or you could have had this backwards. I just did it this way. And then we have the totals here in the margins. Okay, so now what probabilities are actually given? And so there's actually, looks like 3 probabilities given. Which ones are they? And put them at the appropriate places in the table and on the probability trees. Okay? If they fit there. If they don't go one of the places, then of course you can't put it there. But if it will fit in the tree, put it there. If it will fit in a table, put it there. So go do that next. Press pause. Come back when you have that done. Okay, well let's take a look here. The probability that they have the disease is 1%. So that's the probability of the disease here. That's 1%, or the probability of the disease overall is 1% down here. The probability, okay, Test for disease which correctly identify those with the disease 97% of the time. So that says they have the disease, we know it, and then we say that the test works 97%. So the probability that they test positive given they have the disease is 97%, and that goes right here. The conditional probabilities are not in the table here, so that's not going to be directly showing up in the table. And then finally, well, in this one here, the probability that it will produce a false positive is 4%. So that is the probability, let's see, 4%. So that's the probability false positive. That's the probability that they get a positive result on the test when they're actually healthy, that they don't have the disease. So that's going to go down here on a conditional probability on this one. Probability of P given H. And by the way, we're going to work these things not with percentages, but with decimals. So switch them to decimals when you put them in, and you get this right here. And by the way, we always know the total is 1, so that's an easy one to fill out. So there we go. There's the 3 probabilities that we know. And one of them is in the table, and all 3 of them are in the first tree on the left. All right, so let's see if we can start filling out what we can. Okay, so let's fill out the edges on the first tree as much as we can do. So, well, let's figure it out from the table. From the table, we know the sum here is 1, and this is here. What's the one thing we can figure out on the table right here? And where does that show up here? Well, we know these two add up to 1. That leaves, so to find the probability of H, it's 1 minus the probability of disease, because H is just no disease. And so that's going to be 0.99 here, which is the same as putting the 0.99 right here, that these two have to add up to 1. Similarly, these two add up to 1, and so do these. So if you've worked that out, this is 1 minus 0.97 is 0.03. This is 1 minus the 0.04 is the 0.96, and 1 minus 0.1 is 0.99. But again, these conditional probabilities, these 4 numbers don't show up in the table over here, but we do have that last row filled out. Next, what do we do? There's one set of probabilities, 4 of them, that are still missing from this table on the left. They're the ones at the end. How do you find those? Fill those out. Press pause. Okay. Well, hopefully you remembered that to find the probability of the path, we just multiply the probabilities along the path. This is the basic definition of conditional probability, allows us to do that. So we know that 0.01 times 0.97 is the probability that we get both diseased and positive results. Okay, and so forth. We could do that for each one of these. Okay, so 0.01 times 0.97 is 0.0097. 0.01 times 0.03 is 0.0003. 0.99 times 0.04 is here. 0.99 times 0.96 is here. Those 4 probabilities are the 4 probabilities that show up right here in the middle of the table, and those are called joint probabilities. They're the probabilities of intersections of events. Now, what else can we fill out in this table? Well, actually, before we do that, let's do this. Transfer any appropriate information from this tree to the other tree. Well, the one thing that the trees have in common is that the 4 probabilities at the end are the same as these 4, perhaps in a different order. Okay? And so, so you see here we have these just transferred over. This is D intersect P or P intersect D, that probability. It doesn't matter which order we list them in the tree, whether it's D then the P or the P then the D, it's the probability of the intersection at the end. So those are the same. These ones at the bottom are the same, and the 2 in the middle flip, but they're also the same numbers, just flipped around in order. This is P and H and P, same thing here, and then this one goes down here. Okay, next, do the row sum in the table. we can fill out the rest of the table by adding across the rows. How does that correspond to something over here in this second tree? Fill that out now. Press pause. Well, when you add these across here, we're adding these two, we get the 0.0493. What are we adding there? We're adding the two that have a probability of a positive. Well, these two right here are the ones that have a probability of a positive. Diseased and positive test or healthy and positive test. Those are the only two that have a positive in them, so they must add up. First of all, you can add them up because these are disjoint events. So their probabilities can add up. So the probabilities at the end add up. In fact, they all add up to 1 if you add them up. But these two add up to the probability right here. Same way these two add up to the probability right here. That's just doing the row sums in the table here. And of course, these two have to add up to 1. That's just making sure that this column sum at the end is 1. Just like these two add up to 1 is making the row sum there. And of course, or if all 4 of these add up to 1, which is adding all 4 of these at the end here or at the end here, either one of those same numbers, they add up to 1. So hopefully you can kind of see how the table, contingency table, and the trees kind of relate. However, the trees actually have extra information. Down here in the probability table, the contingency table, the white background numbers are the probability of intersections of events. We call those joint probabilities. They're the 4 numbers at the end. But the ones along the margins here are called marginal probabilities, and those 4 things are just simple probabilities. That's the probability of D, probability of H, probability of P, and probability of N, which are these first level probabilities in the 2 trees. Okay? Now, finish the second tree. What's missing in the second tree are all these conditional probabilities. How do we do that? Well, remember, let's look at the first tree. We multiply the 0.01 times the 0.97 to get the 0.0097. So we would multiply the 0.0493, the probability of a positive here, times this missing number, the probability of D given P, to get the one at the end, 0.0097. So the solving that for the missing part, the opposite of multiplication is division. So we just divide. So we take the number at the end and divide it by the one that we're given in here along the path. This would work the same if we knew this conditional probability, but we didn't know the one here. So we could divide this by either one of these two along the way, and we'll get the other one. Okay, so 0.0097 divided by 0.0493, that is 0.19675. And you do the same thing here for the others. These may be rounded off to like 5 decimal places. Some of these may not be exact on the divisions, but at least approximately these are the right values. Again, you can take the 0.0396 divided by the 0.0493 to get the 0.80325, and similarly the 0.00003 divided by the 0.9507 is 0.00032, and the 0.9504 divided by the 0.9507 is 0.99968. Of course, these two coming out of n must add up to 1. So you add 0.99968 plus 0.00032, and that will give you 1. And add these two together, 0.19675 and 0.80325 adds up together to be 1. And we can kind of check to see all the properties of the trees work out here. So, in particular, we're interested in knowing what is the probability that the person who tests positive actually has a disease. So we want to find the probability of D given P, and that's in this tree over here, at this one right here, it's 19.7%. Wait a minute. Does that seem low? Well, it's actually the correct value. So this is good information to know if you're working in a health, let's say you're a nurse, or doctor explaining this, or just a patient who goes in. Person goes in for a wellness test, and they test positive for this. Maybe it's a really horrible disease. Maybe there's not even a cure for it or whatever. Do they automatically assume that they have the disease? Well, not necessarily. There's actually a less than 20% chance that they actually have the disease under these circumstances. Okay, so certainly it's something they should be concerned about and something they should follow up on, do more testing, watch for it, to watch for symptoms and so forth to see if they've got some other corroborating evidence that they might have it. But it's not something they shouldn't do anything like do something drastic, like completely change their lifestyle, or certainly not, hopefully not commit suicide, or do some, sell everything they own, or do something crazy, thinking that they're going to die any minute, because there's really less than 20% chance that they actually have the disease. Now, certainly don't need to overlook it either, okay? But this is a good example of how people can get confused between the probability of a positive given the disease, which is very high, 97%, and the probability that they have the disease given they tested positive, which is less than 20%. So it's very easy to get those two things confused when people are saying it. So it's very useful, to look at these in terms of some percentages or some relative frequencies in a table or a tree like this to make sense of what's going on. So here's another example. Okay, see if you can work this one out. Suppose there's a group of 3,000 athletes. Of these athletes, 200 are illegally using performance-enhancing drugs. Suppose that we have a test that is 90% accurate in identifying illegal use of this substance. That is, 90% of the users will be correctly identified. However, the test will also incorrectly identify 3% of the non-users as being users. Again, complete the two trees and the contingency, frequency, and relative frequency tables for this situation, completely labeling all the edges, pass, and cells. Okay? Now, this one really works exactly like the last time, so I'm not going to go through every detail, but I'd like you to go through every detail, work it out, and then we'll come check your answer here in just a minute. So, or maybe more than just a minute as it takes to work this out. So press pause now. Come back when you're ready. All right, now I'm assuming at this point that you've done this yourself, so let's take a look and see what we came up with. So here are the two trees. Whoops, back up. Here are the two trees here. We have O and A again. And so we have this setup. So a user is going to be O. A non-user is not O. A is test positive. Not A is test negative. You might have used different letters. That's fine. But here's the two trees that are set up. Here are the final answers you can see there. I even threw in the Venn diagram at the bottom with the four joint probabilities, the ones that are at the ends of the trees. Okay? When you do the actual probabilities, they're down here, the relative frequencies here. And then you could actually put that into some actual numbers. Since we have the actual number here, we just multiply all of these probabilities by 3,000 to get the actual frequencies up here. So kind of look at what's happening here. There are 3,000 athletes altogether. 200 are users. 2,800 are not users. There are 2,736 tests should come back negative, and 264 should come back positive. Okay? So of that, that's 180 will be 180 out of the 200. The 200 users, 180 of them will test positive. And of the 2,800 non-users, 84 will test positive. Okay, and 20 of the users will test negative, and of course most of the non-users, 2,716, will test negative as well. And so you can see the percentages. So 6% of the users will test negative. 6%, I'm sorry, that's not 6% of the users. That's 6% of the entire population will test negative and test positive and be users. They'll both be users and who tested positive. 6% of the total population, 180 out of 3,000. Okay, and so forth, and you can see that. Okay, so the conditional probabilities aren't in the table here, they're over here in the tree. So the probability of an A given O, that is, with the letters I'm using, that is, the probability that they tested positive given that they were a user is 90%. 180 out of 200. 90%. But the probability that if you know that it's an A, that they've tested positive, the probability that they're actual user is only about 68%. So if you look at of all of them that test positive, the 264 that test positive, only 180 out of the 64, which is about 68%, are actually testing, are actually users out of the ones that test positive. So you can see how that kind of works together. Hopefully you were able to put all this together. Okay, we'll come back with one more video on similar ideas to follow up with this.